Excellent. Welcome to lesson 4 in our solutions unit on solubility factors. Our learning target for this lesson is based upon the fact that you need to be able to say, I can state relationships for the factors that affect solubility of solutes, temperature versus phase. Yes, so let's get to it. What are the factors that can affect the solubility of compounds? We're talking about solubility in water. Okay. The first thing is the nature of the solute and solvent. That's where the like dissolves like terms come into play. If two nonpolar substances are mixed, they will dissolve. If two polar substances are mixed, they will dissolve. But if you have a polar solute and a nonpolar solvent, they will not mix. No. So nature of the solute and solvent does matter. Okay. Now the phase of the solute. So solids, liquids, and gases. Solids can dissolve in liquids. Gases can dissolve in liquids. Liquids dissolving in other liquids isn't really technically what they're called. It's not really dissolving because they're both liquids. So they're miscible, meaning they can mix, or immiscible, meaning they cannot mix. That's where the polarity, like dissolves like, comes into play. Okay. Temperature is actually our big factor. Solids increases in their solubility as the temperature of the solvent increases. So the hotter the liquid you have, the more solid you can dissolve in it. That's the big relationship. The inverse is true as well. The colder the liquid you have, the less solid you can dissolve in there. Now, it's inverse for gases, because remember, the hotter you make a gas, the more it wants to behave like an ideal gas and become a gas. So the hotter the liquid, the less gas you can dissolve in it. The colder the liquid, the more you can dissolve in it. And you know this intuitively. A cold soda holds on to its bubbles and is bubblier than a hot soda. A hot soda loses its carbonation very quickly, and a cold soda holds on to its carbonation for a bit longer. So there's how temperature affects the solubility of gases versus solids. Now, pressure can affect the solubility of gases only. Pressure only works on gases. Okay? If you increase the pressure on a gas that's in a container with a liquid, that gas will dissolve into the liquid more. So you pressurize the gas, it goes into solution. You depressurize the gas, removing the pressure, it'll come out of solution. That pop top on a soda can, it's pressurized in there to keep the carbonation in the soda. When you pop the top, you're reducing the pressure and the bubbles start to come out. It's the nature of soft drinks. It's delicious, delicious chemistry related to the pressure and solubility of gases. Okay? So saturated, unsaturated, and supersaturated. 3 scenarios. Okay, I'm going to get to the board and describe these. So an unsaturated solution. What you see here is you've got crystals that are in the solid form, and more of them are going into solution than are coming out of solution. Okay, so as that happens, what's occurring is that solid is predominantly going into the liquid. So that's unsaturated. The liquid can soak up more of the solid material, and it's an unsaturated. The other type is a saturated solution. This has dissolved the maximum amount of solid or gas at a given temperature. And what we have is an equilibrium. For every little molecule of solute that goes into the liquid phase, we have a molecule of solute that recrystallizes back into the solid phase. So an saturated solution would appear like it's got a solid at the bottom of the beaker or test tube, and nothing really is occurring. But what is happening is those molecules are going in and out of solution continuously in what we call an equilibrium. A supersaturated solution. This solution has been tricked into dissolving more than the maximum amount of solute at a given temperature. So everything's in solution, even though not all of it should be. We've tricked it chemically. So a shake or adding a seed crystal, as we see in the picture here, will cause a precipitate to form. Addition of the seed crystal into there means that all of the extra solute that's dissolved that shouldn't have been hops on and crystallizes on that seed crystal, and you get what chemists call crashing out, or a precipitation reaction, and all this extra solute just
boom, falls to the bottom. It almost looks like it's snowing inside the test tube, like a snow globe kind of stuff sometimes. Or you see big crystals grow very suddenly. It's kind of cool. I'll try to get my sample example demonstration to work. It's very fickle. It doesn't always work, so fingers crossed. And that's it. That's it for the solubility factors. Things to remember. Nature of the solute solvent. Solid, like dissolves like. Solids increase their solubility with temperature and decrease it with lower temperature. So as temperature goes up, solubility of solid goes up. Temperature goes down, solubility of solid goes down. Gases. As temperature goes up, solubility drops. As temperature goes down, solubility increases. And pressure. If you put pressure on a gas, its solubility increases. And if you reduce the pressure on a gas, its solubility decreases. And then saturated, unsaturated, and supersaturated solutions are relationships with how the particles are moving into and out of solution. And that's all, folks. See you next lesson, which is going to be a little bit longer, focusing on the actual details of table G and solubility. See ya.